It's time we can start now. First of all, I would like to welcome you to this second corporational webinar with IEEE DUTh and student branches across the world, which is going to be recorded and uploaded for later reference on YouTube, and we will mail you the link if you want to see it again. The chairperson of IEEE DUTh is Theodoros Tsiolakis. Hello, Theodoros.
Hello to everybody.
Hi, and we believe that the knowledge you will acquire from this webinar will help you to go further in your career and maybe find some other science parts you like to specialize. In this webinar, we have separated the topics in 2 sessions with a short break between them. Let me tell you some info about our first speaker. Our first speaker is Anna. Anna is a 4th-year computer science student with a minor in economics and IEEE chair in Sarajevo School Science and Technology Student Branch. She will make us an introduction to data science with some practical examples about some machine learning methods, and she will introduce us the game theory concept. So, Anna, you may start. Good luck.
Thank you so much. So let me just share my screen right now real quick. Okay, can everyone see the presentation properly?
Yeah, we can.
Thank you. So I hope everyone is well and staying safe. As you've been told, for my part of the presentation, I will tell you a little bit about data science and what its role in the real world is. So my name is Anna Jamila. You got the basic information about me a moment ago, but other than that, I have conducted an internship in Raiffeisen Bank in the sector of credit risk management, which actually has a huge use of data science in everyday tasks. And other than that, I have conducted another internship in an IT company, which is located only locally for 4 months, but that was only web development. So for the to emphasize the genuine need for data science in business and in everyday life, here's a quote from an English lord back in the early 1900s. He said, I know half the money I spent on advertisement is wasted, but I can never find out which half. And that there is the problem that data science is trying to solve. So in the upcoming slides, we'll take a look at the data science and its life cycle, the main machine learning approaches, some examples of its real-world applications, and then finally the transition into a brief introduction to game theory, which I think many of you are looking forward to. So as for what data science is, it's a field that utilizes statistics and scientific methods along with algorithms and other computer science-related topics in order to extract knowledge from structured and unstructured data. So KDD, knowledge discovery and database, is that discovery process. And I'm sure many of you heard of the term data mining, and that's just one segment of that knowledge discovery process. It includes the extraction of data, data manipulation and visualization, and data maintenance. Data science can be top-down, which means we firstly figure out what we want in the data, and then we conduct knowledge discovery on the data set that we choose in a way that gives us that information that you're looking for. Meanwhile, the bottom-up approach, you have a data set, but you don't know what you're going to get out of it. So you let the algorithm go through the data set, unsupervised with no specific parameters, and then it tells you what it finds, what kind of patterns it finds. And these approaches are reflected in machine learning techniques, which are called supervised and unsupervised learning, which we'll get to around in a few slides. So data mining specifically is probably the most interesting part of the knowledge discovery. And it's actually There are many ways to do it, but for the start, it's been pretty automatized with some tools. So you first need to define the problem, what it is you're looking for. Then you identify the required data and extract it. So you get it either online or through surveys. And then you need to prepare and pre-process the data. And this is the stage that takes the longest to conduct. After that, you can model the data. And this is where you apply the algorithms, which I'll get to in a few slides. And finally, you train the data set, the algorithms to go through the data set, so you can apply the same models to other data sets of similar kind. And lastly, you verify and deploy, which is basically when you kind of extract everything you did in a report and send it to your director or anyone you're working for, a company or whoever. So processing and data exploration is the absolutely most crucial part of the data mining process. Which kind of determines how precise your prediction will be. So you have data types which you need to take into account. They can be categorical or qualitative types, nominal and ordinal. So it's basically you have textual data, you have numerical data, which is numerical and quantitative. Qualitative describes the quality of something, but it can also be something in terms of what hair color is a certain person. So you have something that's not numerical. And numerical can be in an interval, in a ratio, or it can be an integer, which is what I mean by discrete or continuous. Now, when you're looking at data quality, some of the key things that you need to consider with your data set are the accuracy, the correctness, the completeness, consistency, redundancy. So basically, you're looking for if there's anything in the data set that's kind of going to distort whatever you're trying to learn from it. Do you have too many missing values? Do you have some column that maybe people doing your survey did not fill in properly? And are there any inconsistencies? So for the pre-processing, the official terms for many of these are data aggregation, which is the process of you kind of constricting down huge data. For example, you may want to see the price per square meter for your apartment, and you have the price of the apartment, and you have the total area of the apartment. So you can combine those two information into one specific attribute, and that would be data aggregation. Then you have data sampling, which is really good when you have a vast data set that your PC can't really go through in a timely fashion. So you kind of take a sample out of that huge data set, so you would be able to do a prediction model on that tiny sample. So you can choose the data at random. And there are other like stratified and progressive data sampling methods where you kind of limit the way you're extracting representatives out of the data based on their certain characteristics. So, for example, you have a data set in terms of a university, and you want to do a sampling. You want to have this similar ratio of students in terms of their departments. So you don't want to have a sample that only represents computer science students. You want to have them represent the economics, the political sciences, the medical studies, everything in that one sample. Feature selection, feature creation is basically you deciding which attributes you want to look at while analyzing your data set. And if you don't have a specific attribute, but you can derive it from something else, you do that. Discretization and binarization is basically a process where maybe you don't want to have hair color as a nominal attribute. Maybe you want it as 0, 1, 2. So based on how bright the hair color is, where 0 would be the brightest and 3 would be black hair. Variable transformation kind of ties back into everything above. So it's basically dealing with stuff such as America and Europe have a different way of writing down decimal points. America uses DUTh and we use comma. So you kind of make sure that that's consistent across the entire data set. And then dealing with missing values is a procedure in and of itself. So you can remove an attribute if there are too many missing values for each of the records in the data set, or you could find a way to derive it from the other attributes that you do have. So in terms of building the predictive models, now we get to that supervised and unsupervised learning parts. The most used machine learning approaches are classification and clustering, which are pretty much representatives of what supervised versus unsupervised learning is. So classification is, as was seen here, the supervised learning method. So it consists of a learning step, constructing the classification model, and the classification step. So basically, you need to figure out what you want out of your data set. And a good example of this is figuring out whether someone has a risk of developing cancer or not. So that's something that you're explicitly looking for in a data set. So you would have a training data label called the class label, which is basically yes, no, based on what the final result is. So you're looking for a label that's yes or no, and you're looking at the data set where you already know whether a person had developed cancer or hasn't. And then you'll have another data set of other patients where you don't know the final result. So the training set is the one where you're going to apply your model to teach it to be as accurate as absolutely possible when trying to analyze the class label, which is the target in some instances, for example, if you're using Python. And then you're going to have a test data set, which is going to be maybe 20% of the existing data set where you know the final value of the class label, and you're going to test your model. And then you're going to have a final model that you can apply to any new data set of patients where you don't know the final result. Okay, these are some of the examples of classification algorithms. KNearest Neighbors is the most simple one, and one that is most often firstly introduced when going through a data science course. It's basically observing the labels that are of some imaginary number k nearest neighbors of your point in a diagram. And if you have 5 neighbors, for example, that are really close to you in terms of characteristics, in terms of your health condition, in terms of whether you're smoking or not, if none of them, or maybe 3 out of 5 of them do not have cancer, then that means it's most likely that you won't either. And the other one that's really, really often used for the most elementary data sets is decision trees. We'll go through this in more detail, where they go through all of the attributes that you kind of deem as relevant and try to decide how important each of them is. On the other hand, we have clustering. So that is the unsupervised learning method, because you're not telling the algorithm what you want to find. There are no labels. There is nothing that you can specifically say, okay, I want to know this kind of information. You just group data. The algorithm just groups data into clusters based on how similar all of their attributes or some specific selected attributes are similar to one another. So the example I did for my first mini project was actually Pokemon. I took all of their attributes and tried to group them into 3 clusters, which ended up being based on their attack, defense, and health point stats. So you basically ask the algorithm to group the data in an abstract way, and you try to not limit it too much. And then when you get the final result, you can kind of figure out, is there anything valuable out of the patterns that the algorithm managed to find? So the requirements, scalability is basically making sure that you can apply it to data sets that are a bit different from the one that you have been first applying it to. Ability to deal with different kinds of attributes, discovery of clusters with attribute shape. So I'll show a few pictures later on, but basically clusters are often automatically made in a circular way. So it's like an actual cluster, but that doesn't have to be the case necessarily. You can have square shaped, you can have them look like a very thick line. So it's very important that you kind of decide on the clustering algorithm based on what the needs of the project are. ability to deal with data noise is basically when you have some data that's really different from the rest of the data set. So for Pokemon, that would be the legendary Pokemon. They're always somewhere very far off to the side, and they can't be clustered properly into the other Pokemon. Interpretability is basically making sure that whatever you get out of the data, someone that has nothing to do with data science or engineering in general can kind of comprehend what it is that you found. So good clustering results are high inter-cluster similarity and low inter-cluster similarity. So basically, if you have a cluster, you want everything in that cluster to be very similar to each other. And when you have two clusters, you want the difference between them to be very noticeable. So if you're clustering shopping center items, you don't want food and clothing to be in the same category. You want them to be very far apart since they have very different attributes. So again, there are different clustering methods in terms of how you approach the problem and what kind of the attributes you want to take into account and how you want them to be clustered. So there's okay, I didn't put it over here, but there's a KNN algorithm for clustering as well, where you're again basing your decisions on some abstract number k, but in this case, for clustering, you're deciding on the number of clusters you want to have. So this is a visual representation of classification versus clustering, with the classification image representing the decision trees. And in this case, you might, I hope you can see it. Basically, it's the algorithm went through the database and found the most important attributes in terms of the labels that they're giving it. And you can manually give the maximum depth of a tree. And it's so often considered that it should not be too big of a tree. So the depth should not exceed maybe 5, 10 if you're dealing with a very complex data set. But in most simple data sets, 3 to 5 is completely sufficient. And then you have clustering, which, as you can see, depending on the different method, it grouped the data sets into different kinds of clusters. So you want to decide what it is you're actually looking for with those. This is another visual representation of how different algorithms can kind of make a huge difference. So with the Chameleon, it kind of separated based on how dense the points are. And the points are more dense if they're closer to each other in attributes. So Chameleons proved to be very, very efficient over here. Meanwhile, the Cure one kind of, like when you look at it, you understand why it's separated that way, but it does not make too much sense in terms of this specific data set, and you might not want to use Cure. So this was a lot of information for something that's a very in-depth and complex topic. And what I would suggest is starting with a technology, a tool called Rapidminer. It goes through all of these methods, all of these steps, all of these algorithms, and all of the examples in a way that's kind of drag and drop, and no time is wasted on coding itself. But it shows you how each algorithm behaves, what parameters it needs to consider. And then when you feel comfortable with using Rapidminer, you can proceed to actually learn about the technologies that are used in companies used on the market, which are Python and R. And the data sets and challenges can be found on the website called Kaggle. So I can forward this presentation to the colleagues from the IEEE branch, so you would not have to write this down, so you can refer back to this. And this is just a screenshot of Rapidminer. So as you can see, it's very intuitive. So these two retrieve Spring something data set. Spring Bank Drive. It's basically two data sets that have been divided, so I can test and train with different models. You can select the attributes, you can change the type of data. Cross-validation is basically you deciding how many times you want to do that division, 80% to 20%, in order to test how good your model is. So and you just connect it and get a visual representation of the final model. So it's very, very easy to use. You have built-in tutorials, and I would very much encourage anyone that wants to deal with data science to try to use this first. And this is just like a visual representation of a data set dealing with Titanic, like in terms of what is the odds of a person on the Titanic being saved based on the attributes, and it proved that these are the attributes that had the biggest role in a person's survival there. So now for the second segment, the game theory. So this is a branch of applied mathematics which deals with strategic interaction among rational or irrational agents. Agents are basically parties involved in a game. So in data science, it's not that vastly used per se, but it aids in strategic decision-making and outlier detection. So decision-making for the supervised learning methods, and outlier detection is very, very important for the unsupervised learning. So it's used alongside other algorithms to extract value, of course, since it alone cannot generate too much value. And it's used in big data specifically to enhance the models that are already there for business strategies, since you need to consider what the other businesses could do in a specific situation. So it's also extremely utilized in AI for multi-agent AI systems and imitation and reinforcement learning. So multi-agent systems are any system that's not a single agent, single user. It can be the game of tic-tac-toe. It can be the game of chess, which are both competitive games, and we'll get to that in a moment. But basically, it's very utilized in AI more so than in data science specifically, and that will tie into that next presenter's presentation really well. So for data science, it's most beneficial for analyzing payoffs of certain decisions. Again, when it comes to businesses, this is of a great importance, but it's not something that's utilized in every area of data science. So the games are classified as cooperative or competitive in terms of the way you behave. So as we said, competitive games would be chess, would be tic-tac-toe, would be dama. I can't remember the English word for it. Checkers, that's the word. Or cooperative, where you kind of are allowed to discuss with the other person what strategy you're supposed to use. It could be, so one person are a single agent ones, two person and person or any multi-agent kind of game. Zero-sum and non-zero-sum games are basically the situations where either there's no specific way where both, where you're going to be well off, and non-zero-sum games, you have situations where both parties can be very well off. So pure strategy, mixed strategy go into the cooperative and competitive versus zero-sum, non-zero-sum. And I'll give a few mathematical examples in terms of the strategy, since there are several outcomes that each game can have that's very, very optimal for either one party or for both parties. So the most simple example of the game theory is the prisoner's dilemma, and it's probably the most famous one. So for this problem, you need to imagine that you have a partner of crime and you want to rob a store, but you didn't get to rob the store yet, but you got caught trespassing. So the policemen have no proof that you were going to steal anything, but they suspect you. However, they can give you a 1-year sentence for trespassing. This is an abstract situation. It has nothing to do with actual law. But they give you, like they take you and your friend, your partner in crime, to different rooms, and they decide to give you an offer. If you admit that you and the other person were going to steal something, then you get off with no punishment whatsoever. However, the other person, if they don't confess, get 10 years instead of 1. Meanwhile, if you don't confess, but they do, the situation is reversed. If both of you confess, then like you're in a situation where both of you admitted to doing a crime, but you won't get 10 years because you both cooperated, but you'll get 6. However, if you both don't confess, you'll get off with just that penalty for trespassing. We can imagine it's months instead of years because it makes more sense. So this is a two-person game. It's a non-zero-sum game. And as for pure strategy, you'll see that while calculating. But basically, the entire concept here is that you have no idea what the other person can do. It's not someone you're close with. You have no previously arranged agreement in terms of what happens if you get caught. So you're kind of going into this blind. So you need to figure out what is the optimal outcome for you, considering that you have no idea what the other person would do. So the most optimal situation for you would be to confess. And why is that? If you confess and the other person does not confess, you get off with no punishment. If you confess and the other person confesses, they would still confess. So if you didn't confess, you would get 10 months. But this way, if you both confess, you only get 6 months, which is comparatively a better solution than if you kept quiet. So whatever the other person picks, you're better off if you confess. Might not be the best person for it, but it's the most optimal solution for you. Now, Nash Equilibrium is a term that refers to the optimal outcome for both players, where no player has any reason to change his chosen strategy. So basically, everything you know, and you know it's the best strategy to confess, the other person can figure out too, based on these conditions. So the Nash Equilibrium is what I marked in green over here for you to both confess. And this is a strategy that's legitimately used in some specific crime cases, but it's not nearly as dumbed down as the examples in the Prisoner's Dilemma. So another game that's very often used is showing cards. So that's a two-person game. That's a zero-sum game. Since well, you'll see in a bit. And it's a mixed strategy since you have more than one single thing that you can do to reach the most optimal outcome for you. So there are several formulas that you need for game theory in terms of mathematics. You need expected utility for opponent choosing a certain decision, and the expected utility for the opponent choosing another decision, and you need to equalize those two. So the utility basically means the positive side that they would the thing that they would gain from making a certain decision. So in this case, the game goes as if player A shows a blue card and player B shows a blue card, player B will gain 3 points and player A will lose 3 points. The other situation is when player A shows a red card, they get 3 points, but player B doesn't get any points. If they choose the blue card. If player B chooses the red card and player A chooses the red card, then player A gets 2 points, so 2 points, not 3. This is relevant. And if player A chooses red, if player A chooses blue and player B chooses red, then player B gets 2 points, again, not 3. And player A doesn't get any points or loses any points. So this is a more complicated situation where you can't really visually tell what the best strategy is. And this is not a game you can only play once. This is where you can do a mixed strategy. You can repeat this game, maybe best 2 out of 3, best 3 out of 5, anything goes. So to find a mixed strategy, you need to follow the formulas here. F of sigma u is the function of the probability that we make decision 1. So this would be blue card over here. So we input the data from the table into the function. So for utility of player B playing blue, we get the function of our personal utility if we're player A times -3, which is what we would get if that player played blue and we played blue, plus, and now 1 minus our utility function, which is the probabilities, the inverse of probability that we choose that we choose blue, which is us choosing red, and that is multiplied with the other utility, which is 3. And now we repeat the same process for player B choosing red. So here we have, if we choose blue, our utility is 0, and if we choose red, our utility is 2. So we calculate those two, we equate them, and we find our utility function. And this is basically our mixed strategy, how often we need to choose each of the choices. So what we get here is our utility for choosing the first option, which is playing the blue card, is 1/4. And our utility for choosing the red card is 3/4. So basically our mixed strategy is to play the blue card once and then the red card 3 times. And we rotate that every 4 times. And then accumulatively, we will get the best possible outcome we can given this specific situation. And now player B can do the same thing. And as we can see, he gets the same outcome for himself. So when calculating the strategy payoff, we find the mixed strategy and write the probabilities of each player playing each strategy. Then for each of those, multiply the probability of player 1 playing their strategy by the probability of the other player playing their strategy. And then we multiply each of those probabilities by the payoff of the player whose payoff you are calculating. This will make a lot more sense when you see it visually. And the sum of those is the expected payoff of the mixed strategy for the player. So basically, this is another very, very simple example since it's a lot easier to calculate. Basically, you have a husband and wife. Husband likes boxing, woman likes shopping, so they need to decide what they're going to do on the weekend. But if they do separate things, neither of them is going to be happy about it. The woman would prefer going shopping. The man would prefer going boxing. So basically, it's pretty straightforward. So the probability for each outcome is what is the possibility of it happening when looking at everything over here. So you have the man choosing boxing would be 2 over 2 plus 1 was 3, and going shopping is the inverse, 1/3. Same for the woman is the opposite, so she would rather go shopping, so it would be 2/3 or 1/3 for boxing. So now you're looking for the total probability of the two people choosing a certain combination. So the probability for the woman choosing boxing and the man choosing boxing would be 2 out of 9. And then again, for shopping and shopping is 2 out of 9. And then for boxing and shopping would be, boxing. Okay, man choosing boxing and woman choosing shopping. That's 2 times 2, which is 4 over 9. 9 in total. And then shopping boxing is the opposite. It's 1, because 1 times 1. So now, as we said in the previous slide, step 3 is multiplying each probability by the payoff for the player for who you're calculating. So you have here for the man, boxing, so the utility is 2. For shopping and shopping, utility is 1 for the woman, for the man. And then you have this situation where he's not too happy when he's not spending time with his wife. So you multiply both probabilities with 0, since that will make no sense to do. And the same thing goes for the woman, since it's just like the inverse situation where she would prefer shopping and shopping. It would be at 4 over 9. And then for boxing, her utility would be 2 over 9. So now for the final step, we sum up all of those expected payoffs for the player in the mixed strategy. And basically you get that his payoff would be for choosing a mixed strategy 2 over 3, which is less than choosing either options to just agree with his wife. And this is not a competitive game. This is a game where the two are actually allowed to discuss what they're going to do. So if a woman is very, very persistent in going shopping, it would still be better for the guy to agree than to do the mixed strategy where he sometimes chooses to go, sometimes he chooses not to go, and sometimes he kind of like does the opposite of what his wife, and sometimes he agrees, sometimes he doesn't. And same goes for the woman. So it would be a better choice for her to just agree with whatever her guy is proposing than to kind of try this mixed strategy in terms of utility and the benefits she's going to get. So I'm just going to make a short conclusion over here. The reason why all of these segments are very relevant is because all of these different games are something you need to take into consideration when in data science you're considering what a business's opponent is going to do. Are they going to follow the market strategy that your client is trying to put out on the market? Are they going to do something that's harmful to your client? Is it better for your client to kind of make a deal with another company or not? And then for AI, it gets super, super relevant for any kind of decision making, any type of game, since you need to have this logic kind of built into the system in a way that permits the algorithm to make the best choice for itself. Now, that's the end of my presentation. If you have any questions, do not hesitate to ask.
Well, I have one brief question. It's in regard with oligopolies. How actually oligopolies use theory game for their gains? I'm asking as an economics student.
Okay, so an oligopoly is a situation on the market where there's a small number of companies which are dominating the market. So it's maybe 2 or 3 companies that own 80% of the share. And now in some countries, it is illegal for the companies to collude, which means it's legal for them to kind of agree on what kind of price they can set, because that would be discriminatory to the people in that country, since for example, internet service providers, they are a great example of an oligopoly. And if they all set a certain price, then no matter what, the customers would have to pay a very high price, and they could abuse that. But in some countries, there's no law prohibiting that. So in most cases, oligopoly is a prisoner's dilemma situation. So if it's illegal for you to agree with a certain company in regards to what to do and at what point to set the price, you kind of need to go through the prisoner's dilemma situation and figure out which price point would be the most beneficial to you, no matter what the other company does.
Thank you very much.
Any suggestion for projects to practice data science? Absolutely. So one of the projects that helped me get a hang of classification is one that I got inspired in the Raiffeisen Bank. You can get a data set on random clients, imaginary clients. You have it on Kaggle. In terms of what their revenue is, how old they are they employed or not, anything that the bank would have. And then you can try to practice developing a model that will predict whether the bank should give the client credit or not. For a beginner, which is the ultimate path on becoming a machine learning engineer? I would say that other than just going through these concepts, a very, very important thing would be getting a hang of statistics, since it's something that's very, very necessary once you actually get into applying the models. You should learn a bit about business, since all of your clients are going to be companies. Well, most of your clients are going to be companies that do not understand the engineering aspect too well. So they are going to come with you with a problem that they don't know how to solve, but you need to understand which parts of what they're telling you is really relevant and how you can use it in your actual development process. And then another thing, and this is true for not only machine learning, but any kind of actual real world, real market application for development, be it web development, data science, AI, you should utilize the resources online as much as possible, especially since for all of us living in countries that are not very super advanced like Japan is, you need to utilize resources like Udemy. I'm going to write it down in the chat. since you will be in a situation where you're in a company and there's no one in the company that knows a specific thing that you need to do. So you need to learn how to learn on your own, how to look for data on your own. And those are some key things that will help you not only in machine learning and engineering, but in any kind of IT that you decide to go in. You're welcome.
Other questions? Okay, I believe it's fine. Thank you enough for your presentation. That was really impressive. How do you combine data science and the game theory? I recommend you to write on the chat your email if someone wants to ask something extra to advise him or her. So a general question for everyone. Do you want to make a short break for 2 minutes or to continue with our second session? Come on, for 50 euros.
Continue.
Okay. Okay. So let me tell you a few words for our second speaker. Our second speaker is Sotiris Giftopoulos. He is a master's and a PhD holder from the Department of Electrical and Computer Engineering of Democritus University of Thrace. He specialized at opinion and influence diffusion in social networks, and this will also be his session's topic, enhanced by some interesting diffusion models and features, using many things Emma said before as a basis. So Sotiri, the stage is yours.
Hello, everybody. Let me share my screen, my presentation, for a moment. Okay, is it okay? Can everyone see?
Yes, we see it.
Okay, thank you. So in my presentation, I'm going to continue some of the theoretic aspects that Anna presented. I'm going to show you some of some cases of games on social networks and some influence analysis on real-life social networks that are generally in the general topic of opinion dynamics. So Yanis also presented some little things about me. My research interests are influence analysis mainly, which is a combination of opinion dynamics and social network analysis, as well as stochastic processes, since many of the opinion dynamics models, as we will see, involve stochastic processes. I'm currently a scientific associate in the Institute for Language and Speech Processing at Athena Research Center. And if anyone would like to ask me something, please feel free to contact me at my email, which is presented in the slide. I will also write it in the chat. So, in my presentation, we will have a brief look on the field of opinion dynamics, and we will discuss a little bit about opinion diffusion models. I will later on present one of the most prominent opinion diffusion models of opinion dynamics, the Groth model, and present you my research, actually, my doctoral research on influence scenarios based on the Groth model. In the last part of my presentation, I will present some aspects of that are introduced in a social network when stubborn agents act in the network, and we will discuss some of the findings of our research or in the project that we were involved in the case of the Greek news media and political scene. So let's start with the main field, the opinion dynamics, which is a field that was presented in the 19th century by various scientists and philosophers. As you can understand, opinion dynamics has its theoretical underpinnings both on sociology, on psychology, on philosophy, and nowadays in computer science, since it is one of the most trending topics, especially now in politics. We could say that the current form of opinion dynamics constitutes a statistical approach to analyze through quantitative techniques the seemingly erratic behavior of individuals and understand the key mechanisms that contribute in opinion formation. That is something that everybody can understand. I mean, everybody from his experiences or her experiences can understand that in many cases we discuss with our friends and we form our opinions in a seemingly erratic manner. Sometimes our friends cannot understand the way we think and the way that we make our choices. So opinion dynamics studies this process and produces opinion diffusion models, which are mathematical formulations for the process of opinion diffusion. These formal descriptions are the models, and basically they model the opinion propagation in social networks, and they also present some update formulas that can be used to simulate the opinion formation of individuals through time. The basic characteristics of all these models are that the members of a social group act as independent agents. Each member of a group has his own minds and his own behavior, and also have a preset belief on a specific matter. Then the social process of interaction begins, and each member of the social group exchanges its opinion with other members in the group, and as a result, they update their beliefs based on some update rule, some update function. There have been many models presented in the opinion diffusion field. In this slide, I present some of the most well-known models. These models can be categorized depending on the values of the opinions that are used to model the opinions. So we have one-dimensional opinions with discrete values, and this category contains the Ising model, the voter model, the majority rule model, the snatch model, and the Q-voter model. There are also many other models. These are the most well-known. And in the case of continuous values for opinions, we have the Defuant-Weisbach model, the Hexelman-Krause model, the Friedkin-Johnson model, and the Groth model, which we will discuss later on, since it is one of the most prominent models that is currently used in computer science, and it is based on a simple and simplistic yet very efficient basic idea. Its core idea is that each individual has an initial opinion and a set of friends, and he shares his opinions with his friends. So as a result, everyone exchanges their opinion with each other, and then they update their minds, their beliefs. The Groth modeled this procedure using a weighted average process. In this slide, I show you a simple social network, a simple graph consisting of 6 nodes. Each is a member of the community. The arcs represent the friendships amongst the nodes, and the weights attached to the arcs represent the trust factors of each member to the opinion of its friends. As you can see, for example, node 1 here trusts himself. This is defined as self-confidence, meaning the trust of somebody in his own beliefs, and trust also the opinion of node number 3, while on the other hand, node number 4 trusts the opinions of node 2, 3, 5, and himself. Okay? In terms of linear algebra, this process, this social graph, can be represented in a matrix, in an adjacency matrix, as presented in the slide. This is the matrix P, which holds the trust factors of each node for their friends. So the Groth, the researcher, modeled the opinion diffusion model with a simple equation that is presented in the first line next to the graph. He stated that at each time step, the opinion of the nodes are updated based on the trust factors of the nodes to their friends and the previous opinions of the nodes. So it is a very simple equation, yet it is very efficient, and that is why it is mainly used in many researches and in many cases. The underlying mathematical model is a Markov process, a Markov chain, a simple stochastic process. Anyone who attends a course in stochastic processes, Markov chains are the main, the first steps that he has to be acquainted with. So Markov, de Groot modeled his opinion update process, and he studied the convergence of the model. He examined the conditions under which the network reaches a consensus. It is stated in Theorem 2. The main idea is what is described in the last equation of the slide. It states that the final opinion of every node, the final opinion in state of consensus, depends on elements of vector P. P is the left eigenvector of the adjacency matrix P, and can be thought of as the trust factor, the contribution of each node in the formation of the final opinion. This little formula right here, this little equation, holds some very interesting features. It actually states that the final opinion is solely based on the initial opinion of the nodes and on the structure of the network that is contained on the elements of vector P. So regardless of any other aspects, regardless of how long it will take to converge or whatever else happens, the network will converge to the same opinion. So this formulation of the model gives us further initiative to examine its behavior and examine the limits of the process using techniques from other fields. As I showed you before, that the Groth model is heavily related to stochastic processes. Model checking is also a scientific field that focuses on stochastic processes and proposes automated formal verification techniques to analyze such processes. So it was a good idea to start examining the Groth model through model checking techniques. That led us to the formation of influence scenarios on the de Groot model. I will show you two influence scenario, the de Groot influence problem and the de Groot game. In the de Groot influence problem, we have a player, a strategic entity, that aims to tamper with the network, tries to bias the network in order to promote his idea, his opinion in the state of consensus. He has several actions in his arsenal, so he can enhance some relationships, or he can downgrade the relationship between two members of a network, two social members in a social graph. Consider this. It is quite formal here, but consider this as an example of someone trying to downgrade another member of his company, trying to telling lies about him, or trying to limit his influence in the network. In the case here, we have three nodes: node 1, node 2, node 4, and the player chooses to enhance the relationship between node 1 and node 2. That, in terms of mathematics, is implemented by an addition of a factor k. Consider, though, that the update rule in the de Groot model imposes a normalization step in the update function. So the addition of value k in the relation of node 2 to node 1 also affects the other arcs, the other edges, the other relationships of node 2. So node 1 has greater trust by node 2, but then the other nodes also have a downgrade in their trust. In this little example here, we try to use model checking techniques and extract the optimal strategy for a strategic entity that was trying to promote opinion 0 in the simple social graph that was presented previously. Note that opinion 0 is hosted by node 1. The other nodes have an opinion of 0.5, while node 6 hosts an opinion number 1. So he's the rival in this case. The actions of a player are depicted in green arcs. He chose these relationships to enhance by an addition of an element k, which was defined as 0.25. The alteration is also visible in noticeable in the stationary probability vector p prime, which is presented on the third column of the table. You can see, compared to the fourth column of the table p, that the influence factor of node 1 was almost doubled from 0.20 to 0.39, while the trust factor, the contribution, in other words, of node 6 was halved from 0.11 to 0.05. And the final consensus was also affected from 0.45 to 0.32. So we can say that the strategic entity managed to achieve to a certain point his goal. The final opinion, the consensus, was closer now to 0, his target opinion, his favored opinion, rather than in the initial case, which was 0.45. A second example shows the actions of the player when k is has a negative value. That represents actions of defamation of other nodes. So the player tries to downgrade, to disgrace the node 6, which hosts the rival opinion, and then indirectly promote the prevalence of node 1 or node's 1 opinion, which is his favorite opinion. You can see that these actions are the complete opposite from the previous actions, as stated here, but the result is also almost the same. See, you can notice that in the final consensus. Here, the final consensus is 0.32, so the player also achieved, to a certain extent, his goal to promote opinion 0 in the consensus. To make things a little more complicated, we developed the growth game. Here we don't have just one player, we have two players, two strategic entities that aim to tamper with the network, each of the players having a favored opinion, and is urged to to construct their optimal strategies in order to bias the final consensus towards their preferred opinions. Here you can see the example that was also presented in the previous slides. The actions of a player that promotes opinion 0 are the green dust arcs, while the actions of the second player, which promotes opinion number 1, are the dotted blue arcs, the dotted blue edges. You can see that the presentation of a second player acts as a counterweight on the strategy of the first player. The final consensus that is here in the third column of the table, in the column with p double prime, is back on track to 0.46. In the initial state, it was 0.45. The intervention of only one player, player 1, downgraded the opinion to 0.32. And now the introduction of the second remerged the final opinion to 0.46. These are the optimal strategies, and although this example is a small one, it only hosts 6 members, we were able to show that such influence scenarios can be conducted, can be analyzed in greater networks, in networks that have more than 100 nodes in them. So the combination of model checking, the growth model, and the theory of opinion dynamics enabled us to construct such scenarios that were really efficient and could be utilized to examine the behavior of several strategic entities, 2 strategic entities. Nevertheless, these scenarios were not realistic. Remember that we are talking about the growth model. The growth model converges to a single state of equilibrium, of a consensus. So everyone has a unique value. That is not really realistic. In real-life scenarios, not everyone has the same opinion in the end, even after several debates and several discussions. So that can be attributed to the fact that many members of a society are stubborn. They do not update their process. They do not update their opinion. The update process is null for them. They do not take into account any opinions of their friends. They are stubborn, as the word states. Garderians modeled and examined the behavior of such models in 2012 and examined the convergence of such models with the growth model and social graphs with the growth model with stubborn agents. And actually, they stated in Lima that the stubborn agents play a unique role in the equilibrium as they influence each non-stubborn agent according to the relevance, the closeness of each non-stubborn agent to them. They formulated this influence as the hitting probability of a random walk that originated from a stubborn agent I to a non-stubborn agent J. We used this finding in their work to examine real-life scenarios. We focused on the Greek news media and political scene. This research was part of a general project that focused on opinion diffusion on online social networks, led by Associate Professor Pavlos Efremidis. We utilized Twitter for the construction of the social network, and we chose Twitter due to its prominent political profile, and since it was heavily utilized by politicians and news sources in Greece. Furthermore, Greek users have a significant presence in political debates in Twitter. We focused on a subgraph of the whole Twitter network containing Greek news media and political actors. We named these actors as nodes of interest, noise, and I state that that this research took place in April 2018. We chose as nodes of interest the elected members of parliaments, of the current parliament, of the then parliament in April 2018, the MPs, and also well-known news sources with nationwide coverage, such as newspaper, TV channels, and a couple of blogs. The breakdown of the noise can be seen in the slide here. We have 8 political parties. The total number of parties members of parliaments and MPs in Greece is 300, yes. And we achieved to find Twitter accounts of 162 members. We were unable to find any account for a specific party that holds 15 of the back then in April 2018, 15 of the seats in the parliament. The noise of our news interest, the news groups, were 16 newspapers, 6 TV channels, and 2 blogs. So the total breakdown of the dataset contained 186 noise of interest, their followers, which was more than 1 million, and the relationship of their followers to the noise, which was greater than 5.5 million. So we represented this network, this social graph, as a bipartite graph. On the left side, we had the noise, the MPs and the news media, and on the left side, on the right side, we had their followers. So its connection of presented in the bipartite graph represented a follower action, follower-followee action in the real Twitter graph. However, this graph was also of excessive size. The total number of edges were more than 5.5 million. So we had to utilize the projection of the bipartite graph to construct a more concise social graph from the projection on the noise. The technique of projecting can be performed using various projection weighting functions, since each arc that is between noise is based on the follower-followee relationships of the original bipartite graph, and the value computed for its relation is based on several functions. We used a wide range of weighting functions to construct this projection. So we enriched the projection. We enriched the projection with the parties, which are here presented as pentagons, and we connected each MP to the party that they belonged to. So the projection was used as a social network, where the weights of the edges represented the trust of each node to its friends. In some cases, the MPs were transformed into stubborn agents that followed only the opinions of their parties. However, in the initial phase, where we tried to evaluate whether our technique, whether our method made any sense, if we could extract any political information from the projection, we chose to maintain the relationship between the MPs and use a leave-one-out cross-validation technique. What we did in this phase was that we discarded the connection of an MP to its party and used only the connections to other MPs and news media sources in order to evaluate the hitting probabilities, the affinity, the trust factor of each MP to all parties. And we chose to classify each MP to a group according to the greatest hitting probability, to the greatest affinity or the greatest influence factor. Our technique was proven very successful. In this table, you can see the successes in classification, the hits in classification of various projection functions, overlap OKI, which is the cosine similarity function, Jacquard, Sorensen dice. We had a wider variety of projections of weighting functions, and we noticed that almost all of them succeeded in classifying the MPs in the correct group, especially the overlap and the OKI projection function had achieved an astonishingly high success rate of 88.89% and 87.65%. We then chose to use our technique in a more vague problem, a more difficult problem. We chose to tried to approach the notion of news media impartiality, a notion that is also vague for the journalists or the news media scientists. We tried to provide answers to which is the most impartial medium in the political scene. We thought that our technique could be used to establish which is the most impartial medium based on the influence factors that were extracted from the network with the method presented before. Here you can see as a brief definition of impartial medium that is based on the ethical guidelines of the Los Angeles Times, I believe that everyone has a general idea what an impartial medium is. So here, the authors state that a fair-minded reader of the Times news coverage should not be able to discern the private opinions of those who contributed to that coverage, or to infer that the organization is promoting any agenda. So I guess this sums up the basic notion of impartial medium that is in everyone's mind. So what we did is we took the influence factor extracted from the de Groot model using model checking techniques, and we compared our findings with the findings of a survey that was conducted on a group of political scientists. The first stripe here presents the ranking, the positioning of the news media based on the results of the political scientists, while the second stripe presents our findings. The most yellowish part is the most impartial media according both to the political scientists and to our findings. You can see that our method provided solid evidence that our technique is solid. We can extract political information, and also we can successfully approach such difficult projects, such as approaching the news media impartiality in a real-life political scene. Okay? As a general conclusion, before the end of my presentation, I would like to encourage you to continue to work with things that you interest, especially with things that you like to examine in real life, and focus on the topics, on the scientific topics that will enable you to examine furthermore detail in these situations. That was my presentation, and thank you for your attention. Do you have any questions that you would like me to answer? No?
I think you covered all of them. Oh, there's a question.
Well, as I said, how are the weights calculated in a graph? You mean, I guess, in the projection of the graph. In the initial bipartite projection, okay, its weight had the value of 1 in the bipartite projection. In the projection, in the bipartite graph, sorry, in the projection, there were a couple of functions, not a couple, a wide variety of functions used to calculate these weights. These weights depended on, basically on the number of common followers that two nodes shared. There are different formulations of set calculations. For example, the overlap similarity, the similarity that the function that was used and produced the greatest results, is basically the number of common followers divided by the number of the lowest cardinality between the two nodes. The nodes with the node with the lowest cardinality. On the other hand, other metrics use the number of common followers divided by the union of the followers. So there are mathematical formulas that take into account the number of common followers and the rest of the followers. If you would like, I could also send you our publication, which states explicitly its formula and its attributes. You're welcome.
All right, someone else? Okay, so thank you, Sutiri. Okay, there is also a question from Anna.
From Anna. What are some countries in Europe with a well-developed AI sector? To the best of my knowledge, there are really great researchers in the UK and in Northern Europe. In Sweden, I encountered some research papers that were really impressive from universities in Sweden and in Northern Europe. Yes, in UK. Thank you so much, Anna.
I would like to thank you also, Sotiri. Your work is really inspiring for someone who loves the algorithm and the game theory. And I think that it teaches the groundwork of many applications we use every day, like Facebook or Instagram. And because of that, I want to recommend you to see a documentary on Netflix. Its title is The Social Dilemma. I write here on the chat the link to the IMDb to check it out. And okay, so at this point, I would like to thank all of you for the participation and your input.